This recording is about light calculation. What I want to start off with is defining the variables we will be using in light calculation. Lambda is for wavelength. F is for frequency. And E is for energy. So you see that we have three different equations, 1, 2, and 3. And in those equations, we have wavelength, frequency, and energy. We also have our two constants, C and H. Those are the speed of light and Planck's constant. When you are doing these problems, you need to figure out what you are given and what you are solving for to choose the correct equation to solve for the answer. So number one, a radio wave has an energy of 1.55 times 10 to the negative 24th joules. That is energy. And we are solving for frequency. What is the frequency of this radio wave? So knowing that we have energy and we're solving for frequency tells us we're going to use our second equation because the second equation has energy and frequency in it. Energy equals Planck's constant times frequency. Now, we want to solve for frequency. That means we have to isolate this variable. This is h times s. To move h to the other side of the equation, to get f all by itself, we divide by h. Whatever you do on one side of the equation, you must do on the other. So frequency ends up equaling energy over Planck's constant. Now we just type in our numbers, 1.55 times 10 to the negative 24th joules over Planck's constant, which is always 6.63 times 10 to the negative 34th joule second. The joule unit cancels out, leaving you with 1 over seconds, which is the unit for frequency. Frequency is 1 over seconds, wavelength is meters, and energy is joules. So when you type that into the calculator, you get 2.34 times 10 to the 9th, 1 over second. That is your frequency. Make sure you use significant figures. The numbers going in each have 3 sig figs, so our answer should have 3 sig figs. Let's look at the next problem. We now want to know the wavelength in nanometers. Be careful, whenever we use our light equations, the wavelength must be in meters. So the very end of our problem, we're going to fix our units to change it to nanometers. If we are using wavelength and we have a frequency, because we solved for frequency in the last problem, here's our frequency, we have wavelength, we are going to use the first equation, because the first equation has wavelength and frequency equaling the speed of light, which is a constant. Now we want to solve for a wavelength, so we must isolate our variable. We're going to isolate lambda, which means we need to move frequency to the other side of the equation. This is multiplication, so we divide. Whatever you do to one side of the equation, you must do the other. So wavelength equals speed of light over frequency. Then we just write in our numbers and solve. Remember, speed of light is a constant. It is always going to be the same number, 3 times 10 to the 8th meters per second. Our frequency, the S, I got from our problem that we just solved for. This is our frequency because we're talking about the same energy waves. Also, make sure when you're typing into the calculator, you do not write times 10. You use your second comma to get yourself your E's. All right, when I type that into the calculator gives me 1.28 times 10 to the negative first meters. This is our wavelength in meters, because whenever we're using our light equation, our wavelength is going to be in meters. I want my answer to be in nanometers, so I am not quite done yet. This here tells me how many nanometers there are in 1 meter. I'm going to use dimensional analysis. I'm going to take this relationship that 1 meter equals 1 times 10 to the 9th nanometers and write it as a fraction. The unit that I want, which is nanometers, goes on top. So 1 times 10 to the 9th nanometers is on top of the equation. The unit I'm trying to cancel out, which is meters, goes on the bottom. This becomes what I use in my dimensional analysis to change from meters to nanometers. I multiply the number that I got by this fraction, notice the meters unit cancels out. So I take the number that I start with, I multiply it by whatever's on top of the fraction, and divide it by whatever's on the bottom. So it's 1.28 times 10 to the negative first times 1 times 10 to the 9th power. Put that into your calculator, and then divide by 1, because that is the number on the bottom of this fraction. So our very final answer is 1.28 times 10 to the 8th nanometers. That is how we solve for wavelength when we have frequency. The last example is I have energy, and I want to know wavelength. And here I can leave my wavelength in meters because I didn't specify for nanometers. The equation I'm going to use is equation number 3, which is energy is equal to Planck's constant times the speed of light divided by wavelength. So I am solving for wavelength. That means I do not want wavelength at the bottom of the equation. So what you're going to do is you're going to rearrange this equation. What ends up happening is that wavelength and energy swap places. So now I can plug in and solve. So Planck's constant, 6.63 times 10 to the negative 34th joule second, multiplied by the speed of light, 3 times 10 to the 8th meters per second, all divided by the energy given to us in the problem, 4.86 times 10 to the negative 20th joules. Be careful typing into the calculator. Make sure that you have used second comma to use your EU anytime you see times 10. Also make sure that you put everything on the top of the fraction in parentheses before you divide by the bottom so that you are telling your calculator the correct order of operations. When you do that, your answer should end up being 4.09 times 10 to the negative 6 meters. So try that out, practice, and come in for tutoring to ask questions.